The D-type latch overcomes the problem of the RS flip-flop of the situation where it's got multiple inputs at the same value. The symbol, again, we can have a leading or a lagging edge, or positive or negative edge trigger. Symbol, you've got the D input, you've got the clock input, and that feeds to Q and not Q on the output. This is your positive edge trigger. Your negative edge trigger, D in, Q out, not Q out, clock input, but not indicating the negative edge trigger. Now, using logic gates to construct this, I'm going to draw this big. You've got D, that feeds into your first NAND, it feeds into your second NAND, which feeds into Q. Just looking. You got your clock input. The clock input feeds into a NAND at the bottom. This feeds into a second NAND, and then this NAND goes to not Q. Now your clock feeds into both those first NANDs, and your D input feeds firstly into a NOT and then into that bottom left NAND over there. Now on the output over here, again, we've got our crisscross configuration. To form our normal RS flip-flop. Now what this NOT does is it ensures that if whatever I put in there will be inverted so that I've got a condition of a 1 and a 0, or a 0 and a 1 as these two inputs. That'll cause the clock pulse, which is taken as a logic 1, will then force a 0 and 1 configuration at this level. Now again, as a sequential device, we're going to consider how the switching occurs. We've got CLK and we've got D as our inputs. Outputs, we've got Q and we've got not Q, and that right piece there is for the names. Now, when I do not have a clock pulse, my outputs will stay as they are. Okay, the moment I introduce a clock pulse, my outputs are going to change in accordance with the value of D. So when there's a 0 over there, that's going to become a 1, and that 0 over there is going to force this one to become a 1, which means I've got 1, 1 on the input. So whatever the output was, those feedback signals will then force the outputs to remain in that state. Let's check that quickly. Accepting that Q is 0, that means not Q is 1. That 1 feeds back to that point over there. That 0 feeds into that point over there. This 0 over there will force this to be a 1. So that 1 and that 0 forces this one to remain 1. That 0 over there forces this NAND to switch high. That 1 and that 1 will force this output to remain at 0. Now if those were swapped around, then we would have the exact same scenario because of the clock being off. So that output's going to remain what Q is, that output is going to remain what not Q is. There's no pulse there, so again they are going to remain in their hold states. Okay, so that was my red condition. When I introduce a signal, let's put a 1 on D, so we're looking at this scenario over there. That one's going to go in there. When I introduce a clock pulse, that's going to go high, that's going to go high. That 1 and that 1 forces this NAND to switch to 0. That 1 and that, because of this NOT, that's going to become a 0. So that 1 and that 0 is going to force that to be a 1 over there. Now with that 1 feeding back and that 0, Q is going to switch to 1. That 1 feeds back in there. And that 1 and that 1 is going to force not Q to switch to 0. So when I introduce a 1, 1, I will have Q as a value of 1 and not Q as a value of 0. This is my set condition. When I change D to a 0, still with the clock pulse, then that 0 and that 1 is going to turn this NAND output into a high. That 0 feeds in there, which makes that 0 a 1 there, so 1 and 1 there forces this NAND to switch to low. That low switches this NAND into a high on the output. That high feeds back into this input over here. That 1 and that 1 turns this NAND into a 0. As a result, my output condition there is 0 and 1, which is my reset condition.